Here we are. We are in meeting 14, and the topics in this meeting is application of total differential, and especially we will talk about extreme value. Uh, this is total application of total differential. As we mentioned before, that the total differential can be used to approximation uh, the the call the just mentioned in symbol, yeah. The z uh, the z can be used to approximate the value of delta z. So we use this value dz to approximate the value of delta z, where delta z is, for example, we have function z is equal to x comma y. So dz is dou z dou x uh, dx plus dou z dou y dy, and uh, delta z is z2 minus z1. In practice, or in real life, sometimes we have difficulties to find the value of z2 and z1 because maybe the function is a difficult function. So we approximate the delta z by using this formula. And some assumptions should be accepted. The assumption, for example, dx is equal to delta x, and dy is equal to delta y. So this is the assumption we must have. Uh, uh, so our example in the previous meeting said that if dz dx and dy smaller, then the uh, dc will be closer to delta z. Oh my God, some errors in. Sorry, I must fix some error first. Wait a minute. Sorry for delay. Uh, let's we continue the presentation. Here, the application of total differential. Suppose that we want to calculate the volume of cylinders, and uh, the diameter of the volume here, and the height of volume is height of cylinder is here. And so we did it before that this value as uh, the zero wave. This is h zero, and the uh, will be uh, delta d. This is will be uh, uh, delta h. Yeah. Sometimes maybe we use not d but r, where r as uh, d over 2. So we have r will be 3, and uh, delta r will be 0 point 0 15. Yeah. Yeah. This is the exact value of V. V will be P R square H. This is pi 3 square 4. Then we have 36 pi cube. And then if we uh, calculate the absolute error means that we use total differential. The V is do V do R the error, so do V do H D H, and this is the formulation 2 pi R H dH dr, so dr plus pi r square dh. So we replace the value of r h and dr dh we have here, and the result is 1.54, and the relative error is 1.55 54 pi divided by 36 pi. So we have this one, and then we have the percentage as follow. Okay. Uh, Now we want to find the extreme values and saddle points in the function, the multivariable function. This is the illustration of extreme value. This is the function z uh, from x and y variables, and we have the surface, and we can look at that. We sometimes have some tips in the SL maximum or SL minimum. You can look at that here we have uh, two maximum and we have two minimum. The greatest maximum is called as absolute, and the greatest this the what we call the smallest value of minimum is called as absolute minimum. The other might be called as local, yeah, local maximum, and this is a local minimum. Okay. Uh, Extreme values and saddle points, interior point of the domain of a function, where both fx and y are zero, or where one or both of fx and fy don't exist, is a critical point of y. So uh, we say about a point in a domain, and we have that fx and fy is are zero, uh, that don't exist. Yeah, one of them don't exist is a critical point. It means that we have uh, I will illustrate you in one variable like this. Yeah, there is one. My basis here, this one. So this is x is b, and here maybe x a, or maybe here x c. So x a b c is a critical points. Uh, the value of this one, this is extreme value. So uh, it, it, T is called as extreme value. So critical value is where the function will have extreme values. So in three dimension, we also have this illustration like this. This is our surface maybe. And here might be the extreme value in somewhere in the surface, and then the points uh, x and y here, and this is the point, the tip point z, x and y. So this point will be called as critical point, critical points, and the function will be called as extreme value. Yeah, so we have two term. One is critical points, and the other is extreme values. Uh, and some in some case we have a saddle point. Saddle point is uh, yeah, we have critical, but they are not actually as extreme value. Jadi kita punya titik kritis, sebenarnya titik kritis, tapi titik eh, fungsinya bukan nilai ekstrim. Itu disebut dengan titik saddle atau titik plana. Here, the illustration of saddle point in this point, we have uh, uh, in the x and zy here, both of them are 0. So in this case, in this point, fulfill the requirement as the critical points, but this is not extreme values, yeah, because in this point is not maximum or uh, neither maximum nor minimum. So we have this point as a saddle point. And how to calculate extreme values and saddle point? This is the procedure to calculate extreme and saddle point. Uh, First, we must find the extreme, the critical points. Uh, we can calculate the critical points, and we get A, comma B, and then we can determine the value of function will be local maximum at A, B if, yeah, uh, fxx less than 0 and this value greater than 0. And so we can decide f will be its local minimum if the x um, greater than 0 and the, this value still greater than 0. Saddle point is the value of this one uh, less than 0, and we have no decision if this value is equal to 0. Sometimes we can make it short by using the symbol A symbolize of fxx and D symbolize of xx fyy minus fxy square. And so we have this conclusion A less than 0, D greater than 0. So we have maximum or local maximum. Two, A greater than 0, D greater than 0. So this is minimum. And three, we have the D less than 0. So we settle, settle, settle point. And then for we have D is equal to 0. So this is inconclusive. Okay. This is how to uh, find the maximum and or minimum. Uh, First, we must know the boundary. The boundary means that we must know the domain of a function, and then we calculate the critical points. Sometimes this boundary have been given, yeah, uh, have been given, and or sometimes by logic we can say about boundary points of a function. Critical points comes from this function, this equation, and we have points, and the point is called as critical points. And then using this test, this one, this is the conclusion. And if we have this one, uh, the conclusion is local minimum. If we have this one, the conclusion is saddle point, and if we have this one, and the conclusion is there is no conclusion. So we maybe we need another test to find the conclusion. Okay, look at this example. We have the function x squared plus 4y squared minus 4x. So we find the partial the partial derivative of f. We have 2x minus 4, and we must equalize this derivative by 0. Fy will be Fy will be uh, of 8 of y and equalized by 0 also. So the solution of this equation will be x will be 2 and y will be 0. So this is the critical points A and B on the 1 point, 2 comma 0. This is uh, the critical point. Okay, after we have the critical points, so we do the test uh, fx. We this function should be derived respect to x. We have to and maybe xy. Uh, we have that this is derived to by x. We have the 0. And f y, we have that derivative of uh, y respect to y. So we have x. So by using this result, we have that x is equal to 2. Of course, this is greater than 0. We can look at that this partial derivative, second partial derivative uh, is not depend on variables. So we can calculate direct. We can calculate by using this value directly. So this is A greater than 0. So fx times fyy minus xy square. We have that this is uh, 2 times x minus 0 square. We have uh, 16, of course, greater than 0. So we have this one d greater than 0. By using uh, the the result, we can say that uh, f uh, to 0, the function of 0 is minimum local minimum. And this is will be local minimum. Uh, and uh, what is the value? Yeah, because we uh, we uh, we ask to find the extreme value, so we must calculate it. F to 0 means that uh, x replaced by 2, 2 square, plus 4 replaced by y replaced by 0, minus 4. Uh, so we have 4 minus 8, and this is minus 4. So this is the um, local minimum in this example. Okay, this is another example. I make it quick. So we have x is 3x squared plus 9y, and because respect to x, and this is equalized by 0. Fy is minus 3y squared uh, plus 9 9 9x, yeah, 9x, and equalized by 0. And this is multiplied by minus by 1 over 3. This is multiplied by minus 1 over 3, yeah, to make it simple. So we have uh, x squared plus 3y, and this one y squared minus 3 x. And yeah, we can substitute x to the first. We have that x will be 1 over 3 y squared. So we substitute this is to the first equation. We have 1 over 3, sorry, 1 over 3, 1 over 3 y squared square plus 2y 3y is equal to 0. And then uh, yeah, we have here, yeah. And then we have 1 over 9 y square uh, y4, yeah, y power to 4 plus 3 y. And then maybe we uh, simplify this one, we become plus 27 y is equal to 0, and we can solve it. uh, we have y 3 plus 27 is equal to 0. Yeah, maybe we still we need some solution of high order polynomial. I hope you can recite the how to factorize it. I show you uh, while cube plus 27 means we have the coefficient will be 1 0 0 27, and we can make the we can guess the factor based on the factorization of 27. 27 can be 3 times 9, or 1 times 27 plus minus. Maybe we can use uh, 3, yeah, minus 3, yeah, minus 3. So this is go to 1 and multiply 1 by minus 3. We have minus 3. At the column, we have minus 3. Multiply minus 3 and minus 3 will be 9. At the column will be 9. Minus 3 times 9 will be minus 27. And we did, we got uh, the answer become 0. So we have y Okay, this is will be y minus 3, and then this is the result, y square minus 3y plus 9 equal to 0. Um, this is the solution will be we have y is equal to 0, yeah. Y is equal to 0, y1, yeah. Y1 is 0 and y2 is 3. And what about the rest? This is a definite positive. So we can make the factorization. We can factorize them, yeah, because they are quadrat, a definite uh, positive definite quadrat, yeah, quad, quadrat, quadrat. What we say in English, yeah. This is definite positive, yeah. So we have y1 is equal to 0 by using this value, y is equal to 0, then we have x. We can substitute to the original equation, yeah, in this equation or in the second equation. So we have that x1 will be 0, and then by using y2 is 3, we have uh, what we have here, 3x squared uh, plus y, uh, sorry, we can substitute here. We can substitute to the second, yeah. The second we have minus 3 uh, 3 square plus 9x will be 0. So we have x will be 3. So x 3, x2 will be 3. So we have two critical points. The first is uh, 0, 0. And the second is uh, 3, 3. This is critical points. Yeah. So until now, we have that the critical points is uh, 0, 0 and 3, 3. Okay. I will erase it because I have no space more, and I will erase it. Okay. So find the extreme value of function that uh, as we did before that critical points uh, 0, 0 and 3, comma 3. Next, we test the function f xx, as we know from the previous, fx is 3x square plus 9y. So fx will be 6x, and fy will have minus 3y square plus 9x. So uh, uh, xy will be uh, is 9, and y will be uh, minus 6 y. Okay, by using this second order partial derivative, we have uh, for for uh, 0, 0, we can calculate uh, uh, 0, 0 will be 6 0 will be 0, and also f of x y 0, 0 will be 9, and f of y y 0, 0, 0, 0 will be 0, yeah. Minus 6 times 0 will be 0. So we have that a is equal to 0, and we have no uh, clue about the extreme value in this case. D is equal to 0 times 0 times 0 minus 9 square minus 81, and this is less than 0. So we can say that uh, 0, 0 is saddle point, yeah, from the uh, theorem saddle point. So we don't need to calculate it because we just need the extreme value in case of maximum or minimum case. And for 3 comma 3, we have that x 3 comma 3, we have that 9 times 3, we have we have 18 xy 3 comma 3, we have still 9 because they are independent from the uh, so f y y 3 comma 3 will be minus 6 3, we have minus 18. So from here we have a is equal to 18. This is positive, and D will be 18 times minus 18 uh, minus 9 squared. Uh, of course, this is yeah, some big numbers, yeah. 18, we have 4, 6, uh, 14, 18, we have 2, 2, 3, yeah. Minus 2, 3, 2, 2, minus 81. We have minus 4, 0, 3, and this is of course negative. And because it is negative, we say uh, also saddle point, yeah. Oh, of course. Oh, okay. So we have that. I have 3, 3 also saddle point. In this case, we can say that there is no extreme value. but we find only saddle points. Okay. Uh, Now we go to the maximum or minimum problem. Minimum problem. The test of maximum or minimum problem using this test, yeah, same with the example 14.1 and 14.2, but we need to formulate the problem. Yeah. In these examples, the formulation of the function have been given here, the function, the function. Yeah. But in a real life or in some problem, the first is we must find the formulation of x and y. So this is addition steps uh, to find the maximum or minimum problem. So the steps to solving the maximum and minimum problem is we must determine the variable related to the problem and determine the equation. So this is what is x, for example, what is y, for example, or what is z, for example. So we must determine independent or dependent variables. So uh, in the second, we must know what is the relation of them and the equation occurs from the first step. So this is must be known. And the third, we must find the maximum or minimum values by using second derivative test. Yeah, there are some example. This is the example. Uh, girl, uh, and uh, we have length and girth, and then find the largest. I will uh, give you the another problem. Yeah, I will solve for the another problem, and for this problem, uh, I leave it for you to do by yourself. And this is another uh, problem or another topic. So maybe the last topics. We now can solve constraint maximum or minimum. Means that we have two things in the formulation. Uh, we must have a main function. Main function is, so for example, z is equal to r depend on x and y, and we have constraint, yeah, subject to or constraint, subject to or constraint. Sometimes the uh, the uh, constraints contains uh, g, x, y, and z. Uh, in three variable or two variable. Yeah. So this is the construction of the problem in constraint maximum or minimum. Okay, sorry, maybe this is only two variable. Yeah. Yeah, this is the constraint maximum or minimum. We can use Lagrange multiplier or by using Lagrangians. And what is the formulation? If we have main function, two variables, and the constraint problem can be constructed by become here. And so we must have Lagrangian function like this. we add fx plus lambda g, yeah, lambda g. These variables is called as Lagrange multiplier. So why we say this is as a Lagrange function. And then by using this function, we must find the critical points. So find the critical points. Yeah, by using the derivative of x respect to 0, um, derivative of g respect to y, and derivative of g respect to lambda is equal to 0. So uh, we must solve this equation. And then find the maximum or minimum by using second derivative test. Yeah. Second derivative test. Okay, after we get it, for example, here we have three positive real numbers, and whose sum is 120, and product of three numbers is as large as possible. So our objective is objective. Our objective is we must find uh, the 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 function where uh, the function is multiplication of x, y, and z. Yeah, for example, we say it we need it this product as large as possible, and subject of, of, of concern subject to uh, x plus y plus z is equal to 120. So we want to use Lagrange function, and so first is uh, we must move 120 in the right to the left. So we have x plus y plus z minus 120 is equal to 0. So this is the function f x, y, and 0. And this is the function g, yeah, g, x, y, and 0, and z. And then Lagrange function Lagrange function will be this is a Lagrange function function. So we have g, x, y, z, and one more variables lambda will be x, y, z, the main function, plus lambda times x plus y plus z minus 120 is equal stop here. We have this is Lagrange function. Okay, we want to find the critical points. Critical points gx. Gx means that we must derive this function respect to x. We have yz, and this is will be lambda, and we must equalize by 0. gy, and the same procedure. We have xz plus lambda is equal to 0, and gz we have xy plus lambda is equal to 0. And the last, we have that G lambda will be, yeah, because this is multiplication, well, we have that x plus y plus z minus 120 will be 0. Now we have four equation and in four variables. So we need to solve it. Yeah, there are many alternative ways, yeah, to solve it. Uh, One of them is we have same value here minus yz, and this is also lambda is equal to minus xz, and this is lambda is minus xy. So we can equalize two of them here, two of them. For example, here we have minus yz will be equal to minus xz. If we have here, we can say that uh, yz yz is equal to xz, and assume that uh, z z is not equal to 0. We can cancel out z. We have y is equal to x. And what about we have the opposite, z is equal to 0. If we have z is equal to 0, the problem is not too interesting because uh, the value of function will be 0. So we have the assumption that z is not equal to 0. And also by using uh, this equalization, we have minus xz is equal to minus x y, and we have the same procedure here. We get that uh, z will be equal to y. And now by using 1 and 3, yeah, 1 and 3 here, we have minus yz is equal to minus x y, and also uh, the conclusion is x will be equal to z. And by using this all of this conclusion, we can say that x will be equal to y will be equal to z. And uh, we can substitute this conclusion uh, to the last equation. We have that 3x, yeah, because y is equal to z and equal to x, so we have 3x minus 120. 120 will be 0, so x will be 40. And because of this x is equal to y equal to z, so we have that y is equal to 40 also, and z is equal to 40 also. Uh, if we have Lagrange, if we do the maximum or minimum by using Lagrange function, we don't need to use the second derivative test. Yeah, we don't need, yeah, because the conclusion always that must the conclusion must be extreme values. So we don't need to do a second derivative test. Ya, ini keuntungan menggunakan fungsi Lagrange, ya. Kita nggak perlu melakukan uji turunan kedua. So this is the conclusion. We have that F uh, uh, 40 at the critical points, 40 and 40. In this case, this is critical points, yeah, critical point. So the function will be 40 times 40 times 40. So this is the maximum value, yeah. What we have, uh, 60, 90, 99 volt, yeah, maybe here, uh, in volume unit, yeah. So that's all the uh, topics we must discuss in this in this meeting. The rest is exercise. The exercise, I will give you the clue to solve it, but you can make it detailed by yourself. For the example one, you must find Zx and Zy first, yeah, Zy first. So find the critical points. Yeah, might be the critical point more one or more than one. Yeah, the critical points. Find the critical points. And then after you get the critical point, use the second derivative test. Derivative derivative test. Yeah, so you get the extreme values. Okay, this is number one, and this is maybe yeah some uh, mm, give you the formulation. So the distance square, we have this function. The distance point is square of distance. Uh, is x square plus y square plus z square. Yeah, this is a standard to the center of coordinates, and the this is a subject. Yeah, the subject. We need to get the minimum values, and uh, the sorry, subject. This is objective, yeah, or the main function, main function. The subject or constraint is uh, x plus 2y plus 3z is equal to 6. And you can use Lagrange function here. Lagrange function to solve this problem. Okay. This one, we must need to formulate the problem. Uh, we have rectangle box without a top lid. Yeah, so it means that we have a rectangle, uh, but there is no lid, yeah, in the top. So the if this is I, Y, and Z, uh, the, 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 uh, they cover only five plane without top lip. Yeah. So we have xy plus 2yz plus 2 xz. This is the cover, yeah, the material, and the material must be uh, 12 meter square, and we must find the largest volume. So the function will be x, y, z. Yeah, this is the the objective. Yeah, the objective value, and this is the constraint. Yeah. Again, after you get the formulation, yeah, you can use Lagrange function, and as we uh, do in number two. Yeah. So this is the constraint, and this is the function. Okay, again, number four, you already have the function and the subject. So you can say that uh, the function x squared plus y squared, and the subject will be y plus 3x minus 3 is equal to 0. So g, x, y, and lambda will be x squared plus y squared plus lambda y plus 3x minus 3, and then you must find gx, gy, and g. I did it in the previous example. So the procedure is similar, are similar, and please use this procedure to solve the maximum value or maximum value of the function subject to uh, another equation. Yeah, I give you some process of this problem. Gx will be here 2x, yeah, 2x, and this is plus 3 lambda. We equalize by 0. Respect to y will be 2y plus here plus lambda is equal to 0, and g lambda will be y plus 3x minus 3 is equal to 0. And then please find the maximum or minimum. Yeah. In this case, of course, we must have minimum. Yeah, maybe we select it. Yeah, this is number 4. Okay, number 3. Number 5. This is uh, how to find the error of the columns box and its relative factors. This is as we did in previous slide. Also, we must find V, we must find dV as a approximation of delta Z, and then we must find dV divided by V. Yeah, so please did it as we do in the previous. But we must know about the formulation. A rectangle box has length 20. Measure of error is this one, right? 15, and measure of n this one. and height is 10 also. X will be 20, Y will be 15, and Z will be 10. The volume is the formulation of volume is X, Y, and Z, and delta dx will be uh, 0.01, dy is 0.02, and the z is 0.01. And okay, after you get all of this stuff, all of these things, please find the v, dv, and dv over v. Yeah, you must remember that dv is the dou v dou x dx plus dou v dou y dy plus dou v dou z dz. So please find dv and the relative. Okay, there are lots of another exercise in two plus slides, and please do it and solve it to prepare for the examination. To okay, that's all. So, stop servers. Okay, that's all, Jerry. And thank you for coming for this class. And I will send you the links of these recordings after this class. And uh, have a nice weekend. See you in the next occasion. Thank you very much, Sherry, and good morning.